So having discussed the structure of the state space of two-level quantum systems and having seen some physical examples of two-level quantum systems, let us now move on to the next aspect that we are interested in, and this is covered by postulate 2, which talks about physical quantities or observables associated with quantum systems. How do we describe physical quantities or observables, right? Before we get into this, again, there are certain concepts from linear algebra or linear vector spaces that we must invoke. In particular, we need to understand certain specific kinds of linear transformations. Remember, we said that these vectors, states are vectors, so they transform according to certain linear transformations, and we already saw an example of this in the way the 0 and the 1 basis transform to the plus and minus basis via a matrix transformation, right? In the matrix representation, it was a 2 by 2 matrix, but more generally, this is a linear transformation, right? So these linear transformations occupy a special place in quantum theory, obviously, and there are two kinds of linear transformations. So we will also often refer to them as linear operators, right? There are two categories of or classes of linear operators that we'll be interested in, namely Hermitian operators and unitary operators. So we will restrict our attention to two-level systems or finite dimensional systems, so we can basically associate these operators with matrices, right? So if I am thinking of a qubit system, then I want to understand what is a 2 by 2 Hermitian matrix. If I am talking about a D-level quantum system or a D-dimensional space, then I would like to know what is a D cross D Hermitian matrix, right? So Hermitian matrices or Hermitian operators have the following property. So a matrix H is defined to be Hermitian if it is equal to its complex conjugate transpose. This operation, complex conjugate transpose, is often simply denoted by a dagger symbol. So this is a dagger, and this operation is called the adjoint operation. It's called the adjoint of a matrix or the adjoint of a linear operator, and the adjoint is simply the complex conjugate transpose. So take the complex conjugate of the entries of the matrix, take its transpose, and if that resulting matrix is equal to the original matrix, then such a matrix is said to be Hermitian, right? So these are also often called self-adjoint matrices or self-adjoint operators, right? The second class, so why are Hermitian operators important? We will just observe two things about them. So firstly, Hermitian operators or Hermitian matrices have real eigenvalues. This is one reason why we'll be interested in them. And just to again recall what the eigenvalue is. So when H acts on a vector V in the following way, that it simply gives a scalar times the vector V itself, then we say that lambda is an eigenvalue of H and this ket vector V is an eigenstate. The state corresponding to ket V is an eigenstate of this operator H, right? So this is just a recall from linear algebra. So Hermitian matrices have real eigenvalues. Secondly, Hermitian matrices are diagonalizable. What this means is that they admit a diagonal form in some orthonormal basis. Remember, there are several bases that we can construct for a given vector space, right? And so the associated matrices that we will write for operators will also be associated with a particular basis, right? and we will see examples of this shortly. But the idea is that Hermitian matrices are such that there exists some orthonormal basis in which this matrix can be simply written as a diagonal matrix. Remember, a diagonal matrix is one which has entries only in the diagonal and nothing in the off diagonal. So, this is an example of a 2 cross 2 diagonal matrix, right. So, this is the first kind of operators that we will be interested in, Hermitian operators. So, let us construct or let us write down examples of Hermitian operators for two-level systems or two-dimensional linear vector spaces, right. So, let me write down some examples of Hermitian operators and then we will come to the second postulate, right. So, here is an example. I am going to call this as the operator S sub z, okay. This will be written in units of the fundamental Planck's constant, right, which is h bar. H bar is simply the Planck's constant h over 2 pi, right. So, I am writing this matrix in units of h bar by 2, 1 0 0 minus 1, right. This is a 2 by 2 matrix. It is easy to check that if I take the complex conjugate, the matrix is the same. I take the transpose, again the matrix is the same. So, the complex conjugate transpose is simply the matrix itself, and of course, this is a diagonal matrix with real entries in the diagonal. So, it is expected that this matrix must be Hermitian, right. Similarly, one can write down an operator or a matrix of the form Sx. Again, I put this constant here. So, this constant here is basically to give some physical dimensions to this, because very soon I am going to associate a physical quantity with these matrices, okay. This has the physical dimensions of the Planck's constant. Okay. For now, you can just think of this as some number that is multiplying this 2 by 2 matrix. So, this is the second 2 by 2 matrix that I want to consider. Once again, we can check that the adjoint of the matrix, which is nothing but the complex conjugate transpose, the dagger is equal to Sx itself, right. So, these are just some examples of matrices that satisfy this property. This was a diagonal matrix and this is an off diagonal matrix, both of which are Hermitian. So, why are Hermitian matrices important in quantum mechanics? And that is where the statement of postulate 2 comes in. So, the second postulate says that physical quantities, what are called observables in quantum theory, are associated with Hermitian operators on the system Hilbert space. In particular, the eigenvalues of the Hermitian matrix or the Hermitian operator is associated with the possible values taken by the corresponding physical quantity. So, physical quantities or observables are associated with Hermitian operators. The dimensionality of the system space will tell you what will be the dimensionality of the Hermitian operator. These are Hermitian operators on the system state space, and the eigenvalues of the Hermitian operator are basically the set of possible values that this physical quantity can take. Again, let us contrast with the classical scenario. We said system is described by some set of position and momentum values. Any function of position and momentum is a valid physical quantity or observable for the system. But in this case, physical quantities must be associated with specific kind of operators, namely Hermitian operators. The set of possible values that this physical quantity can take are simply the eigenvalues of the Hermitian operator. So now we see why physical quantities must be associated with Hermitian operators, because it is Hermitian operators who have real eigenvalues, right? And so since the eigenvalues represent the physical values of some observable, we need observables to be associated with Hermitian operators. So recall that Hermitian operators have real eigenvalues, and so this association then makes sense that physical quantities will take on one of these possible values. So what are these two operators that I wrote down here? So again, let's revisit the two-level system. Now I am going to talk about the particular two-level system, namely the spin-half system. So while I will describe postulate 2 and maybe postulate 3 with reference to spin-half systems, whatever I say here holds for any other two-level system. It's just easier to talk in terms of spins, observables and spin values, right? So consider the spin-half system, and we said the spin can take two possible values, right? The ket 0, let's say, corresponds to the plus half value of spin, and ket 1 corresponds to the minus half spin state, right? Now, remember this matrix that I wrote down here, which is of the form 1, 0, 0, minus 1. Let us see what the action of this matrix is on ket 0. So remember that ket 0 is associated with the two-column vector 1, 0, and ket 1 is associated with the two-column vector 0, 1. So what is the action of this matrix or this operator Sz on ket 0? I hope you can work this out and see that this actually does not do anything to the state, it leaves the state invariant. So this is simply h bar by 2 ket 0. But now, so similarly, let's just write down the action on 1, and again I leave it for you to check that Sz acting on ket 1 will be minus h bar by 2 ket 1, right? But now these two equations are essentially they are essentially eigenvalue equations, right? So it appears that ket 0 is actually an eigenstate of Sz with corresponding eigenvalue h bar by 2, and ket 1 is an eigenstate of Sz with eigenvalue minus h bar by 2. So now we can make the physical association that Sz must be the observable associated with the spin along a particular direction. So since I call this z, let's just say the spin along the z direction, right? Because if you remember, when we map these states to the block sphere, the 0 and 1 were the states along the z axis. So let us say that Sz must be the observable associated with the spin along the z direction. The spin along any direction for a spin half particle can take one of two values, right? So it can take one of two possible values, plus h bar by 2 and minus h bar by 2, and there are definite states associated with these values. So if the spin half particle is in state ket 0, then the spin takes the value plus h bar by 2, and if the spin half particle is in the state 1, then the spin along the z direction takes the value minus h bar by 2. So this is an example of how we associate a certain Hermitian operator with a certain physical quantity, namely in this case the spin of a spin half particle. What about the second state? What about the second Hermitian operator, right? Sx. So let us look at Sx. What is the action of Sx on ket 0? I leave it to you to check that Sx acting on ket 0 will not give you an eigenvalue equation. Rather, Sx acting on ket 0 will give us h bar by 2 ket 1, and Sx acting on ket 1 will give us h bar by 2 ket 0, right? So this is easy to check. Once you take this matrix representation 1, 0, and then you act this matrix on the 1, 0 state, and then we see that this gives us these two states. So now these are not eigenvalue equations. So we can no longer make this association for Sx. So what kind of physical observable is Sx? The answer lies in identifying the eigenvalues and eigenvectors of Sx. Action of Sx. So I suppose from these two equations it is sort of clear that if I make a superposition of 0 and 1, then maybe that state will be left invariant by Sx. So let us say what is Sx acting on Ket plus, right? And of course Ket plus is of the form 1 by root 2, 0 plus 1, and then you see that this gives us 1 by root 2, h bar by 2, 1 plus 0, but 0 plus 1 and 1 plus 0 are the same. So this essentially gives us h bar by 2 Ket plus. So now we have an eigenvalue equation for Sx. Similarly, we have an eigenvalue equation for the minus state as well. So this gives us minus h bar by 2 Ket minus. So once again we see that what we have identified the two eigenvalues. So these are both eigenvalue equations. So we have identified the two eigenvalues, namely the plus h bar. So this the h bar, as I told you earlier, is giving units to the spin, right? So this is plus half in units of h bar, minus half in units of h bar, right? But now along a different direction, right? So now along a different physical direction, and once again this is the reason we call this Sx, because if we associate 0 and 1 with the z axis or as spin states along the Sz, then we can associate plus and minus as spin states along Sx. So Sx is the observable corresponding to spin components along the x direction or the x axis, right? And once again the spin for a spin half particle in any direction can take on one of two values. So this is again plus half or minus half in units of h bar by 2, right? And then the associated eigenstates are Ket plus and Ket minus. So Ket plus is a definite spin state, which is namely the spin plus half state along the x direction, and minus is the spin minus half state along the x direction, right? Alright, so we have given examples to illustrate the second postulate, namely how observables can be associated with Hermitian operators. The values that the observables can take are associated with the eigenvalues of these Hermitian operators, and the corresponding eigenstates correspond to states with definite values for that observable. To go back, the 0 and 1 state, you see, while they have definite values for spin along the z direction, they do not have definite values along the x direction, because they do not satisfy eigenvalue equations for the Sx operator, right? Okay, we will come back to this when we revisit measurement, but this is just a point to note here. So finally, let me also write down these matrices in the outer product notation. Sz can be written as h bar by 2, 0, 0, minus 1, 1, right? And this is another feature of the fact that the 0 and 1 are eigenstates of Sz. You see that Sz has a diagonal representation, right? And so when I write down the outer products, there are only two outer products that feature here. The cross terms 0, 1 and 1, 0 do not occur in this expansion, right? So we do not need them in this expansion. So it's only the diagonal terms, right? And this is again reflective of the fact that 0 and 1 are eigenstates. Now if I write down Sx, right, remember I am writing, so the fact that Sz is diagonal in the 0, 1 basis means that I am writing down all these operators in the 0, 1 basis. This is just another point to note. the Sx in this basis does not look diagonal. In fact, it has exactly these two off diagonal terms which did not occur in the Sz outer product representation, right. Now again this can be checked just by doing a bit of bracket algebra. We know what 0 and 1 look like in terms of plus and minus. We know what plus and minus look like in terms of 0 and 1. So one can then write this out essentially as plus plus minus minus minus. So you can check that these two expressions are indeed the same. These two outer product representations are indeed the same. I have just simply gone from one basis to the other. I started this segment by saying that there are two kinds of linear operators which become important in quantum theory. One is the Hermitian class of Hermitian operators. The second is the class of unitary operators. So let us now change tracks and move to discussing unitary operators. So unitary operators are those which satisfy the following condition: when I take the complex conjugate transpose of the matrix and I multiply it with itself, then it gives me the identity matrix. Remember, the identity matrix is just a matrix with 1 along the diagonal entries and zeros everywhere else. Similarly, U multiplied with U dagger is also identity. So, if a matrix U satisfies this condition, it is said to be unitary. That the matrix times its adjoint is the same as the adjoint times the matrix is equal to the identity matrix, right. Actually, we have already seen an example of this in the previous segment. Recall the H matrix which we wrote down, which had this form 1 1 1 minus 1, and recall that H acting on ket 0 gave us plus and H acting on ket 1 gave us minus, right. Now what is H adjoint? Well, H adjoint is basically the complex conjugate transpose. I take the transpose, I get the same matrix. These are all real entries, so I actually get the same matrix. So H to begin with is Hermitian, right. But the property of H that will be most useful for us in subsequent lectures is the fact that H is also unitary. So let us check that. So let us multiply H with H dagger. That is the same as H squared because H dagger is the same as H. So that gives us half times this matrix product, and I hope it is easy for you to check that this indeed gives me 1001, which is the 2 cross 2 identity matrix. So here we have an example. So of course one must also check that H dagger H satisfies this, right, but that's kind of obvious because this is also H squared, right, and so this is also identity. So this is an example of a 2 cross 2 unitary matrix, okay, or it is a unitary operator acting on two level systems, right. So why are unitary operators important in the context of quantum theory? And that brings us to postulate 3. And this is the postulate about time evolution, right. So how do quantum systems evolve with time? Well, if psi of t naught represents the state of the system at time t naught, then the state at time t is obtained by the action of a unitary transformation or a unitary operator on the initial state. So let us call this unitary operator U, right, and U basically is the operator that maps or transforms the state at time t0 to the state at time t. So this is how it is denoted: U t comma t naught. The first argument telling you the starting and the second argument telling you where the time at which you're stopping, the time evolution, so to speak. So it maps system at time t naught to the state of the system at time t, right. So this is the third postulate on time evolution in quantum mechanics. Quantum states evolve with time according to a unitary transformation. So why are unitary transformations important? One can understand this at various levels, so one can sort of give two explanations for this. So the way the time evolution postulate happens is via a certain Hermitian operator called the Hamiltonian. This is a term that many of you might have heard. So the Hamiltonian, and this is often denoted H again, is a Hermitian operator associated with the energy of the system. The physical quantity that the Hamiltonian represents, it is also a Hermitian operator, just like Sx, Sz for the case of the spin-half systems, but H is a Hermitian operator that is associated with the energy of the quantum system. And Schrödinger equation tells us the time evolution equation, the differential equation that is satisfied by quantum states as they evolve with time is the following. The partial derivative with respect to time of psi t is actually given by h times psi, where h is the Hamiltonian. So it is the energy description of the system which comes from the Hamiltonian of the system that decides how the time evolution happens. And the way we get to this unitary operator is by solving this equation, and for the case where h itself does not depend on time, is independent of time, for simplicity we may assume that. We are not going to dwell on this aspect much in this course, but I just want to mention this, that the solution to this equation essentially looks like this, that the state at time t is given by the exponent of the Hamiltonian operator t minus t naught by h bar, and this exponential of the Hamiltonian is what becomes the unitary time evolution operator. So this is just a remark. You can think of this as just a remark or something to sort of complete our picture, but we will not really dwell upon this much or take exponents of operators and so on. But suffice it to know that the famous Schrödinger equation, which talks about time evolution of quantum systems, is what leads to this description of a unitary operator as the time evolution operator, as the operator that transforms the state of the system from one time to the other. Another sort of mathematical way of understanding why the time evolution or transformation must happen via unitary transformation is the following. So now let us compare the inner product of the initial state with itself rather than, so this is the norm of the initial state, right? And because the initial state is a valid quantum state, this norm must be 1. Now what is the norm of the final state? Right? What is the inner product of the final state with itself? Well, remember the final state comes via the action of this u acting on psi of t naught. So let's try to work this out. So the first part is the bra of this. So I can take the dual of this equation or the bra of this equation, and that will look like this, right? So bra psi is, remember when I take complex conjugate, I actually must invert the order in which these terms arise. So this actually looks like psi of t naught, the bra of psi of t naught times, I must take again the complex conjugate transpose of u, right, which is nothing but u dagger, right. The complex conjugate transpose of u is nothing but u dagger. So this is what the bra version of this ket equation looks like. And when I substitute that here, I get psi of t naught u dagger u psi of t. But remember that u dagger u, because u is a unitary operator, is nothing but the identity operator. And the identity operator does nothing to any state. It's the operator that leaves every state unchanged. So this then gives me, I'm sorry, this should be t naught as well. So this gives me psi of t naught, which is nothing but the norm of the initial state, which is 1. So the key takeaway from this is that unitary transformations preserve norm, or they preserve the length of a vector, right? So unitary transformations preserve the norm or the length of a vector, and that is why the time evolution must be governed. So this is a kind of, you can think of this as a kind of mathematical constraint, that time evolution must indeed happen via unitary transformations. The final point that I want to make here is these unitary transformations, which constitute time evolution, are indeed the bread and butter of quantum computation. They are the quantum gates that transform quantum states. So let us now get back to thinking about computation. So quantum gates are essentially unitary operators or unitary matrices. And since one is thinking about qubits or two-level systems, one can say that single qubit gates, that is gates acting on a single qubit, are essentially 2 cross 2 unitary matrices. And we've already seen an example of this in the form of the H gate, and I said that this is the Hadamard gate, right? And remember that the H actually had the following matrix description. It looks like 1 over root 2, 1, 1, 1 minus 1. And this is a very important gate in the context of quantum computation and also quantum algorithms. And this is a gate that in some sense generates a superposition between 0 and 1, throws 0 and 1 into an equal or a uniform superposition of 0 and 1. Okay, I just want to finally conclude by observing some properties of this unitary time evolution transformation. So this was just one time evolution, right? One step, let's say from T0 to T. What happens if I want to evolve from T0 to T1 and then T1 to T2, right? So the first thing to note that U of, let's say, T2 T0, which is time evolution from T0 to T2, is actually composed of the product of this form. So we first have T0 going to T1 and then T1 going to T2. So it's actually a product of this form. So the sequence is that T0 is less than equal to T1 less than equal to T2, right? Now this has an important consequence in the context of quantum gates, right? So if I want to do multiple operations on the qubit, I simply have to stack up the gates in this fashion, right? So I may want to first do a Hadamard gate and then do some other quantum gate operation and then do a Hadamard. So this is how I will stack up. This is a sequence of gate operations where each of them is some unitary operator, right? So this is how a sequence of quantum gates will look like in the matrix representation, right? The second thing to note, of course, is that when I evolve from T0 to T, I have the unitary matrix U, but what I can also think about now is U dagger, right, which is the complex conjugate transpose of this. Now that actually corresponds to a time evolution in the reverse direction in some sense. So that actually corresponds to going from T to T naught. So this then leads us to the fact that if I apply a quantum gate on a quantum state, and then I would like to undo the action of that gate, then I simply have to apply its adjoint operation, because gates are unitary matrices. So what this is saying in some sense is, if I have a unitary matrix U, then its complex conjugate transpose is its inverse, right? This is the inverse of the transformation or the gate, right? And so all quantum gates in that sense are reversible. This is a huge departure from the classical setting, where there are very special gates which are reversible. Not all classical gates are reversible, but in the quantum case, all quantum gates are reversible. So we'll stop this segment here, having discussed postulates 2 and 3, which talk about physical quantities associated with the quantum system, their representation in terms of Hermitian operators, and finally time evolution in terms of unitary operators.